Okay. Last bit we have here is expression trees. So expression tree is a way to represent a math equation. All right, so sample 2 plus 4 will become the tree with 2 and 4 as the leaves and plus as a node combining those two together. All right, so what we do is we take operands and turn those into leaves, and then join leaves together, the corresponding operator. And doing so with operator precedence in mind. Right, so if we do a post-over traversal on the tree, their corresponding mathematical expression will be equivalent. So here, if we do post-order, we'll have 2, 4, and plus, right, gives us for 6, just like we have with our infix notation. Right, so the operator precedence from the perspective of the tree is the subtrees evaluated first, giving back a numerical expression, which can then be fed back into the higher layers. The tree. All right, so let's do a bigger expression, 2 plus 4 times 6. All right, so the first step, we will create our leaves. Try to get them lined up here. All right, 2, 4, and 6. All right, so based off the operator precedence, we'll have to join these together based on our precedence order. So 2 plus 4 would not happen before 4 times 6. So we'll go ahead and do our multiply to join together 4 and 6. Then we can go ahead and join our 2 subtrees together with our addition. All right, so if we were to break this tree down first by its subtree, 4 times 6, and 4 times 6 is 24. And then we have 2 and 24 after that. Oops. And because that subtree just evaluates to 24. And then we can proceed from there. And then just transforms into 26. All right, so key thing when doing this, do not mirror things. The order in which the operands exist in the expression is the order in which the leaves should exist. It's just a matter of combining the operands together based off their operator precedence. Right, so if we have the same expression as we had before, except change the operator precedence by wrapping the 2 and 4 with a plus, our resulting tree is going to be different because we will go from left to right as we build out the tree when the operator precedence is equivalent. Okay, so like before, just go ahead and create nodes for each leaf, where there's going to be 1 leaf per operand in the expression. And we can start joining them together. All right, 2 and 4 will add together because they are a subtree with our operator precedence. And then the multiplication will happen afterwards. All right, so if we go ahead and do our post order. All right, we get 2, we get 4, then the addition, 6 comes along, and then we'll multiply. All right, which gives us 2 plus 4 gives us 6, and then a 6 and a multiply, and the resulting answer is 36. All right, change the expression, you change the tree, and the corresponding math that results from that can also change. All right. I suppose I should drop the expression first. Let's see. Can't sync my changes. Okay. How's my voice coming through? Am I glitching out?
Sounds
All right.
good to me.
You're coming through loud and clear.
Good. Just little bugs with Google. All right. All right. So 1 plus 2 times 3 plus 4 minus 5. Right, 5 operands, 5 leaves. Now it's just a matter of joining things together in the proper order. Right, so plus, plus, and minus all have the same operator precedence, but we do have our multiplication. It does need to happen first. So we'll go ahead and join 2 and 3. And we can go from there. So we'll work our way left to right. All right, so we have everyone else has the same operator precedence. We'll just build up left to right. 1 will be added to the result of 2 times 3. And the result of which we'll just add 4 to. And then lastly, we'll subtract off 5. And we can redraw this to get the levels a little bit clearer for what's going on. But how we happen to be drawing the tree and the actual tree structure is not changing anything, right? So we have a subtraction way up at the root. And we have our addition, all fun stuff. So I'm just gonna line things up here a little bit better. Right, so this is our resulting tree. First 2 times 3 will happen. Right, so we do our post-sort traversal. All right, 1's our first leaf, then 2, then 3, then multiply becomes a leaf. We add 4, add 5, subtract. All right, so we'll have 1 and then 6 on the stack. After our multiplication, then we'll have our addition, gives us to our 7. We'll add again, and then we'll subtract 5 off from that, giving us 6 as our final answer. How are we doing with our expression tree? Does it make sense?
Yep.
All right, so just a minor way to double check. At least math is right. You post-sort traversal, then apply reverse push to the traversal, check the math. All right, so let's look at some incorrect expression tree. Basically, it's just reversing things or getting operator precedence wrong. All right, the expression is 1 plus 2. And we create a tree. That's 2 plus 1. We have a problem. All right, if we try say 2, 1, and then we can add those together. Mathematically, we're good because the result's still 3. That's just because the operator is cumulative, right? So if we were to swap addition to subtraction or division, we can see that the math becomes wrong all of a sudden, which means the tree we built was also wrong because what the operator is shouldn't matter because the algorithm should be predictive as to what we're building. So if the expression is 1 plus 2, right? It's 1 operator 2. So what we want is the same 1 and then whatever the operator is. Then 2, right? So this is wrong. So let's go ahead and fill that in. Wrong. Right, the way you can go wrong. We add more text here. Back. Incorrect. All right, so the way you can go wrong is getting the math wrong. So we go back to similar that like we had before. 1 plus 2 times 3. If we do the 1 plus 2 first, then the math doesn't come out to be 7 like it's supposed to. That's right, 1 second. Okay. All right, so 1, 2, 3 lines up. If we start joining things incorrectly, we'll see that the math also falls apart. There. Add those two together and then multiply the result. All right, when we do a reversible expression on this, we'll see that the math isn't producing the result that we're expecting. All right, so this was our incorrect step here. All right, post-over gives us 1, 2, add that together, 3, then multiply, which takes us to 9. And the correct answer is 7. All right, I think we got one last thing, just to make sure we're good. That's making sure we are good with the difference between, all right, to visual representation. All right, so any tree can be represented with an array. It's just only common for heaps to be that way. All right, so whatever our data happens to be, just be somewhat arbitrary at the moment. Yeah, 14, what have we used there? 5, 4, 6, and 15. All right, so the corresponding drawing the root is our first. Let's see, get both these up here at the same time. Yeah, that's fun. All right, try that again. Yeah, no changes. Okay. All right, so whoever's at index 0 is our root. All right, so 5 is the root. Its children are at 2 times I plus 1 and 2 times I plus 2. All right, so children are 2 and 3. 2 and 3 are our children. And we got a lot of nodes. Let's go ahead. Drop out next level, right? 2's children. Who's at index 1? Right? 2 times 1 is 2 plus 1, right? 3, and then the next one after that, 7 and 9 are the children of 2. 3 at index 2. All right, so 2 times 2 gives us 4 plus 1, 5 for our left child, right? 11 and 1. Left and right child. And go a little crazy there. My copy paste. All right. And then we'll have a few more data points. Just add those in. Where are we at 1? We still got pretty close to full leveling. All right, so let's fill it out. And we'll delete any extras that may be left over. All right, so I can keep doing the math here to get where we want, but since the table is pretty full up, right, I can just start ripping through the numbers, right? 0, 8, 14, 5, 0, 8, 14, 5, right? Those are children of 7 and 9. We have 4, 6, and 15. 4, 6, 15. All right, so if we want to go back the other way, take the tree and I'll just go ahead and call a few of my branches here. Want to go from the tree to the array. Same idea, just doing the math in the reverse order. Shouldn't the right child be 7 and 8? 7 and 8. Okay, hold on a second. The right child of 2. Oh, I started doing my numbers wrong, didn't I? Oh, 7. Yeah, let me double check did my numbers right. 5, 2, 3, 7, 9, 11, 1, 0. 5, 2, 3, 7, 9, 11, 1, 0, 8. Ah, thank you. And I typed 5 when it's an 8 there. There we go. And 4, 2, 5, 4, 6. Yep, there we go. Typo. Thank you for catching that. All right. All right, so we have a root at index 0. And we have its 2 children, 2 and 3. Here's where it gets a little fun. You want to be careful when you have voids. All right, 2 has its left child, who is 7. 2's at index 1. 2 times 1 plus 1 gives us our 3. All right, then we have empty right child for 2. Then we jump over to 3. 11 and 1. Then we have 0 and 5, not to get a typo like last time. And here we have 2 more dead spots from 4, right? 4 gives us 9 and 10 as indices, so these spots are dead. Dead. Then we have a dead spot 11. 11 has the left child, and then we have 6 and 15. Okay, so when we get around to the trees test in 2 weeks, the tree might be a drawing, or the tree might just be an array. I tend to lean towards the arrays because images like to break and become problematic. So the arrays tend to have fewer problems. on the test, I can do either way. I can do both. I can give you, here's the visual and here's the array, and you can tell me what's wrong with the array type thing. Or I can ask you what value should be at index 5 based on the drawing. Or we could do math. Who are the children of 1 type thing? So here's the value 1. You can calculate who the children are if they are in the table. All right, so between now and next time, or now and Friday, the practice test for test 3 will be up. Apparently I'm missing practice test page for test 3, so I'll have to go find out what I do with that and or add it. It's gonna be all trees, right? So all this section 3 stuff. Make sure you have your terminology. Remember who the root is, what level is, what tree height is. Remember in our convention, tree height, an empty tree has a height of -1. We'll be building trees of more or less any type that we talked about. But that's pretty much it. Any questions at the moment for the test? Well, you can correlate an expression tree with the reverse Polish by doing a postfix traversal on an expression tree. So they're related in that way. But you can also view it like reverse Polish because there's no, once you're in the expression tree, there's no longer any operator precedence with the way we're doing it, because you have an operator and it has 2 operands, which are its 2 children, or which are either leaf values or subtrees. And if those subtrees are more than just a leaf, you just need to evaluate those first, right? So operator precedence is enforced by the structure of the tree as opposed to actually looking at the operators themselves. Now, question: if I have pre, post, and indoor traversals on the test? Yep, any of the traversals. Test 3 is in 2 weeks. All right, so I will next few days refresh those details so that it will show up in the syllabus. Right, because remember I have 5 tests in the semester plus the final, so roughly every 3 weeks, 3 to 4 weeks, we'll have should have a test. No, you could do a traversal on an expression tree any way you want. Right, so let's look. Let's grab that one and then do the other traversals. It's just post order is more useful. In order can give you problems. With operator precedence. So in order, right, we have 1 plus 2 times 3 plus 4 minus 5. So that gives us back to where we started. And pre-order minus plus 1 times 2, 3, 4, 5. That's not a 5. There's a 5. Right, so depending on the tree, I think in order might go sideways sometimes if I recall correctly. Let's grab the good old Wikipedia and Okay, got live chat. All right. Wikipedia. Let's see. All right, they have all the traversals there because it's a tree. You can traverse it with any traversal you want. It's just the post order is most interesting for us as that goes hand in hand with our reverse Polish. No, you could do any traversal. Yeah, you could do any traversal on an expression tree. Post order is what we'd use to validate that the expression evaluates to the same value as we had with our infix notation. Right, doing infix traversal, depending on the actual tree, generally gives you back the original expression, but then, you know, validating too much. Okay, let's see. So we'll check our labs, make sure things are all right. So we got graphs up. Okay. Will we be covering any programs for expression trees? No, we don't do any code for expression trees. Right? It's just a binary tree. So that's all of why it's interesting, just because it's a good example of tree, and it's one of those places where we can correlate it to other data structures and algorithms, which is why it's that particular binary tree is discussed as opposed to one of the others. I mean, there's all kinds of other binary trees. In fact, let's talk about that. And there's red-black trees. I just spaced on the other. Let's see, does I have time about that? This one. Let's see, general tree, binary tree, that's fine. That's not what I'm looking for. There we are. Right, so lots of other tree structures, red, black. Display tree, that's what I was trying to remember earlier. These are the trees as you get to advanced data structures. Get in there, and you see it's one of our class of self-balancing tree structures. And self-balancing is what you want for a tree. Otherwise, it's really, really, really far from being of any practical value, because an unbalanced tree gives you not such great. Ooh, 1985. That's pretty new, relatively speaking. A lot of things we talk about are quite a bit older. And as I start getting into graph theory, things are going to get really old. (1736). Yeah, graph theory has been around for a long, long time. All right, so trees are actually all graphs. They're just directed acyclic graphs. So it's a graph that has no cycle. Vertices and edges. All right, so we're calling them nodes and edges with trees. We just toggle over to graph theory to call them vertices and edges. Right, so I have 1, 2, 3, 4, 5, and 6. These are vertices or points in the graph, and then they are connected by edges. So a graph, like we have here, the simple graph, 1, 2, 5 is a cycle because I can go from 1 to 2 to 5 and right back to ourselves. That's a cycle. 1, 2, 3, 4, 5 back to 1. That's cycle, right? There's numerous cycles that we can create here. That allows us to start somewhere and then spin back to where we began. And that's what separates just graphs in general from trees, which is a subsection of graphs, because they are directed acyclic graphs, right? Because when we're drawing edges of trees, it goes from root to its children, if it has any, in a directed form. Whereas when we get the graphs, this edge between 6 and 4 is bidirectional unless we start drawing some edges in here, or arrows on these edges. Right, so 6, 4, and 4, 6 are an shared edge together. Okay, let's start creating some whiteboards. Oh, typing. Overrated skill. Go. There's the link in the chat. All right, so new section 4.0 graph theory. All right, so a general graph is a collection of vertices and edges. There must be at least one vertex, and there may be 0 or more edges connecting a pair of vertices, or a vertex to itself. All right, so vertex, all right, it's just a point in the graph, also known as a node. Typically, vertex is labeled or named. All right, an edge is defined by a pair of vertices. Edge cannot exist apart from a vertex. Right, so set of vertices. V, right, could be just defined, come separate list. Right, A, B, C, D sort of thing. And then our set of edges. E, just define the sets as pairs, A, B, B, C, C, D, and then DA. We'll just do a simple cycle graph here. All right, so our graph, just G, which was our set of vertices plus set of edges. All right, so for the most part, we'll not be doing much in terms of notation here. Curly braces and all that fun stuff. Yes, you can totally have a pair of vertices as a graph with nothing connecting them. All right, so let's do some example graphs. Yes, the degree of those vertices would be 0. All right, so I won't bother labeling them to start. We'll just go ahead and just throw some boxes up here after we're done. Those can be connected. Those can be unconnected. Three. All right, let's try to get a box. And Have to do some reordering here. Okay. Eyes. Fun background noise. And go. All right, so these are all examples of graphs. All right, so all graphs as they are at the moment, but we'll go ahead and connect some edges just so that we can have a little bit more than we have at the moment. And then sometimes the edges are going to be directed. Right, so if there is an arrowhead on some of them, then that goes only one direction, but if there's no arrowhead, then it just means both ways. And doesn't matter. These are not the arrows I was going for. Let's try again. If things are disconnected, what is going on here? All right. So this is a graph. This graph is disconnected. A disconnected graph just means there are subgraphs within it that are not connected to other parts of the graph. Right? Whereas our graph over here, that graph is connected because I can start at a vertex and then find my way. I can create a path by hopping along edges to get to all the vertices in the graph one way or another. So there exists a path. Most of the time, we're going to be dealing with connected graphs. But they could also be disconnected. All right, let's get a new doc. And talk about graph types or categories. All right, simple graph. Here we have our vertices, set of vertices, set of edges, all edges go both directions. All right, so the edge AB is the same thing as BA. All right, so all graphs are presumed simple in the class unless otherwise qualified. All right, so we'll just draw a few simple graphs. All right, there's our first one. All of one vertex. Do another one with a pair of vertices. And that'll be good enough. Right, so no arrowheads on any of the vertices. Directed graph. Same as a simple graph, except one or more edges have direction. In a digraph, the edge AB is not equivalent. The edge BA. Right, so we might draw direct graphs in a little bit of a lazy fashion by omitting the direction of the edges. It's the same thing. That's just how we're drawing it. All right, so we'll need at least 2 nodes here, but we'll do the same graph or similar graphs a few ways. Let's do it that way. All right, let's give an arrow. All right, so here's a couple graphs. Let's label these. All right, so this graph is not the same as this graph. And fix it in a second. All right, so these 2 graphs are different. And let me actually add another vertex. Let's add C so we can make it obvious that this is a digraph in all 3 cases. All right, these 3 graphs are all the same. All right, so let's do this notation form. We have collection of vertices AB and edges, which we have just AB for that one, and our second one, our collection of vertices are the same. 2 vertices, both labeled A and B, but my set of edges is different. It's just BA. All right, here, my set of vertices A, B, and C. And my set of edges. And we have A, B, B, A, and C, A. Which is exactly what we have over here. And exactly what we have over here. They were just drawn a little bit differently. Might note convention, alphabetizing vertices and the edges. Does help in trying to compare. Sorry, AB. Yeah, so in our first example, we know this is a digraph because there exists an edge that shows an arrow. All right, so from looking at the visual representation, we can see it's a digraph because there's an edge showing an arrow. And if we don't draw arrowheads, that just means the edge goes both ways, just like it does with a symbol graph. We could draw that same edge with just putting arrowheads on both sides, or we could draw them as separate edges, right? Which it is. If we look at our set of edges, we have an edge AB, right? So there's my AB, and we have an edge BA, And there's my edge BA. Right? It's sometimes easier to see it's a directed graph just by looking at a set of edges, because a simple graph would not bother saying A, B, BA. A simple graph would just say AB, because AB and BA are the same thing. So if there's an AB, you would not find a BA if it's a simple graph, because we'd say AB as opposed to BA due to our convention of alphabetizing. A weighted graph. A weighted graph applies labeling or naming or weights to the edges of the graph. This can be applied to a simple graph or to a digraph. Right, so unless otherwise specified, weighted graph is built on, 1 second. All right, weighted graph is built on top of a simple graph. All right, so in simple weighted graphs. Okay. All right, here I'm not going to bother labeling the vertices because that's not the part we care about. It's the edges that we're going to apply some numbering to. Okay, type. That's right. All right, so we say that that edge is 5, some arbitrary value, that edge is 2, and that edge is 4. What this means is we're saying that there's a transition cost. The question is a simple graph same as an undirected graph? No, a simple graph is, as an undirected graph. Yes, an undirected graph is a simple graph. Right, so with the weighted graph, we're just saying that there's a cost to transition from one point to another or there and back again, right? So home, school, 5 minutes, 5 miles, $5, Uber, whatever the data is representing, that is just a cost to get from a point to point inside the graph. So same thing here, whatever these points represent, costs 2 to transition from this first point to the second, and 4 from the second point to the third, and then the same going back. So a simple graph, the costs or the weights go either way. Right, other places, the things, this could be like what the latency is between LA and Las Vegas for a particular network connection, and Las Vegas to Tucson, wherever it is that these points in the graph represent. Right, so example, directed weighted graph. All right, so here we're gonna have to be more particular about the edges. All right, if there's just one direction here, right, it costs 5 to get from that vertex to the other vertex. But if there's going to be both directions and the costs therefore those transitions aren't the same. Arrows going the right way here. We just need to go ahead and do extra labeling, right? Cheaper to get there than it was to get back, or cheaper to go back than it is to get there for this particular one. Whatever it might be. Okay, let's get some underlines in here. Keep our sections in order. All right. Next, we have a multi-graph. So this is a graph. Graph will allow multiple edges between a pair of vertices. Sorry, fumbling around with my screen here. Simple multi-graphs. All right, so we'll start small. LA to New York. Yeah, apparently I'm not using a monofont type. All right, get bigger, bigger. There we go. So let's go with 3 is good enough. All right, 3 ways to get from LA to New York. We can fly at 6 a.m., 8 a.m., 12 a.m., right? We don't know what these edges represent. We just know that there's multiple ways to get directly from LA to New York. All right, might swing by Houston on the way. And there could be multiple options going that way as well. All right, might as well make these separate. Separate examples, right? It's not very often that you're going to find just multi-graph, because what's the point in having 3 edges between these without any data that's going to differentiate these? All right, so more often you're going to see a weighted multi-graph. Multi-graph. Yes, multi-graph. All right, so we'll just go ahead and take our previous one, just start adding some data points. Whatever the numbers are going to represent. All right, could be miles, could be dollars. Bonus points you get for booking that particular flight. It's all sorts of different things that the data might be representing. Flight time. Whatever it is, it's something that our search might need to make use of when figuring out ways to go. Let me get rid of an edge or 2 here so I can keep my text boxes easy to go, right? So you got your 6 a.m. flight, it's $50 from LA to New York. But you got a 9 a.m. LA to Houston, and then at 2 p.m. from Houston to New York for 25. So if you want to save $10 and add a couple hours of flight time, travel time, There's alternate routes that you might take. So there's a lot of various right. So we're gonna be looking at some algorithms that are going to take data like this, figure out what's the best way. What is the shortest route from LA to New York? Because the direct route isn't necessarily the shortest route when you're measuring on dollars, right? What's going to be costing you the least amount? And sometimes there may not even be direct routes for your particular carrier. So it's all going to be hopping through one or more airports. So then you might be just sorting my travel times. Lots of data points that can exist in here. So there's lots of ways that we can analyze that same set of data. Pseudograph. And this graph allows single node loops. You'll find these used in finite state machines or automata. When you take, or if you've already taken your priority, familiar with the FSAs, they'll use a pseudograph to represent the states that the machine can be in and what will transition it through the states. And there's going to be a pseudograph and it's going to be weighted and it's cost weighted multigraph. So we're going to be combining several different characteristics that a graph can have and then creating a finite state machine from it. Effectively, whenever you're creating a program, you're creating a finite state machine. It's the initial state. I've got no data, various states that come in where the user has provided data, and then we go ahead and churn through and spit out the result, and machine's done. Often, just do a vending machine. All right, so I'll just put a link in there for you so you can check it out. Because they are related, right? To graphs, all that fun stuff. There's a simple one, right? And they can get more complex depending on how complex the machine is. All right, so not tested on this, but an area where graphing is very much used. All right. Let's jump over to memory representations. Graphs in memory. Right, so there's two ways that we're going to look at it in this class. Two ways. Represent a graph in memory by looking at the adjacency of vertices. Right, so two vertices are adjacent if there exists an edge between the two. Right, so we can use matrix to represent who is a neighbor with each other. Or we can use a list structure. It's going to be an array of lists. Right, so these are known as adjacency matrix and adjacency list, right? That's kind of a bit of a misname since it's adjacency lists. Right, so for a simple graph, use a binary matrix where 0 indicates there is no edge between a pair of vertices, and a 1 indicates that there is. Gratch, I don't know what a Gratch is, but let's make that a graph. All right, so we'll label each axis of the matrix with the vertice names, vertex names. And we'll do so in alphabetical order. Okay, let's do a nice simple 3 vertex graph. Go ahead and create ABC. All right, A, B, and C. A connects to B, B connects to C. So we'll go ahead and create a 3x3 matrix, A, B, and C. A, B, and C, for both the horizontal and vertical labeling. A does not have an edge connecting to itself, so we'll put a 0 for A to A. A to B does have an edge, so reading down the row, A connects to B, via that edge there. So we'll indicate that with a 1. A does not connect to C, so we'll indicate that with a 0. B does go back to A because it's a simple graph. So put a 1 there. B to B is a 0. And B to C as a 1, right? B has 2 edges connected to it. So that's what's known as the degree. The degree of a vertex is the number of edges touching it. And the term for that is called incidence. Incidence is an edge connecting to a vertex. All right, C does not connect to A. It does connect to B. And it does not connect to itself. And so double checking. Graph has 2 edges. Since it's a simple graph, each edge goes both ways. So we would have 4 cells with 1 or true set. All right, so double check. I got 1 for vertex A, I have 2 for vertex B, and I have 1 for vertex C. All right, so over here, let's talk about the degrees. Degree of a vertex. This is the number of edges connected to it. So in this graph, A and C have a degree 1, B has a degree of 2. All right, so cross-checking matrix, a cell, just like an Excel, right? This cell. So there are 9 cells in the matrix. All right, so cross-checking the matrix for row A. 1 entry is on, which is the degree. of A. For row B, 2 are on, also representing the degree of B. Same for row C. Can also read by column here, since we have a simple graph. Right, and since it is a simple graph, you will have a mirror across the diagonal. Right, so these ones match up, these zeros match up, and these ones match up. Have a nice mirror across the diagonal with a simple graph. A mirror across the diagonal. Okay, so same graph. This time with an adjacency list. And we'll just drawing. So we'll go ahead and A, B, C. Is our top level array. And the way the adjacency list works is each list keeps track of which other vertices it connects to. So A connects to B. So we'll have B in its list. B connects to A and C. So we'll have A and C in its list. And C just connects to B. All right, so what you want to pay attention to here, let me add some text. All right, A's list has as its neighbors just B. B has as its neighbors A and C. And C has as its neighbors just B. Right, so the common mistake people make trying to read this, or we look at the linked list and we see A pointing to C. Right, but there is no edge in this graph from A to C. This says they have nothing to do with each other. The only relationship they have is the fact that they come from B's list. So at the top level, it's an array. The element type of the array is a linked list. Each one of these is linked list, and just like with the matrix, the lists are sorted. All right, so just like with the matrix, the array is sorted and the lists are sorted. That gives us consistency as well as performance improvements, because now we can binary search the array and we can cut traversals of the list off once we know we've gone past where the solution exists. So there's a question: the left edge vertex, the left edge vertex comes first, and then the right side of the vertex, or it's just random. Let me redraw. Grab the graphic again, put it over here. All right, so we had 3 vertices in the graph, so that's how big the array is. And the vertices are labeled A, B, and C, so A, B, and C. B does connect to C. See, we have B here in the middle. B connects to A and C. So we have A and C in its list. A connects just to B, so we have just B in its list, and C connects to just B, so we have B in its list. So it's very much like the matrix. Right, so A, and 0 for A, 1 for B, 0 for C. So we have nothing for A, nothing for C in its list. For B, A and C are on, so we have A and C in its list. And for C, we just have B on, so we have B in its list. Okay, let's take a peek at the graph matrix lab, and then we'll take a break. No, so that's right. So for the adjacency list, let's do another one. Example 2. And let's make this disconnected. All right, so ABC, so it's a fully disconnected graph. And the corresponding adjacency list would be, we have nobody as neighbors. No neighbors, no neighbors, and no neighbors. If we go ahead and build up from here, and we connect A to B. All right, so it's a bidirectional edge, so we're going to have to add 2 entries. And we get this box. All right, A goes to B. And B goes to A. And C is disconnected. All right, so the lab, we're doing graph matrix, right? So adjacency matrix. Going to prompt the user for how many vertices there are. Then you're going to label the vertices ABC, apple, banana, chipmunk, whatever. If you want these to be single characters for the names are fine. The matrix that we build is a square matrix because that's how adjacency matrix works. For each vertex, that's going to exist on the horizontal and it's going to exist on the vertical. I will point you, so you're going to want to use a jagged array in C++ here. I will repoint you to a Stack Overflow link I should have somewhere. Should I do this, right? It's an array of arrays. Syntax is kind of a little bit cumbersome in C++, but it is what it is. For arrays, so you'll ask the user to define a pair of points, and then they will just set them up, right? So user says they want 6 vertices, they label them all, so this just goes into a string array. A, B, C, D, E, F. You can assume that the user is going to alphabetize them for you, but for the purpose of the lab, it doesn't much matter. And you'll ask them to start adding edges to the graphs, right? initially you have a 6 vertex graph that is fully disconnected because there aren't any edges between any of the vertices. So you're giving the user the ability to add vertices, and same line, 2 lines, whatever, is just white space separated. They say vertex, then they say another vertex. Which is you go to your array of strings and find where that matching name is, right? So index 0 for A, and B is the index 1, and you just go into your matrix and you turn on 0, 1. Right, so if you do it as a simple graph where A, B is BA, or you do it as a directed graph like here in my example, as them being separate, either way, it's fine. It's just adding a line of code or getting rid of a line of code, depending on which way you did it. And then a loop, just loop across the matrix. If you find a cell that's on, you grab the name of the vertex from one index for the row and one index for the column, and then you can spit out, you have an edge, then keep iterating through the matrix and you have spitting out all the various edges that you have. Right, so just all arrays. Yeah, you can just, the examples has it as an undirected graph, but if you want to do it as a directed, well, sorry, the example has it as a directed graph. If you want to do it as an undirected graph, either way is fine. Right, with a undirected graph, you're just doing 2 sets. You get your matrix x, y equals 1, and then yx equals 1 type thing. So directed is less code, undirected is more code. Right, because with directed, you just iterate across the matrices and you spit out both directions of the edge because they're not the same edge. With an undirected graph, if you spit out AB, you should not spit out BA because that edge has already been printed. So you want to do a directed graph. So otherwise, you actually, it's not that hard. You just need to, your nested loop needs to start skipping down where it starts. So that actually goes through 1/2 of the matrix. But we can tweak and play with that later. Okay, so we'll go ahead and take a 5-minute break. That takes us to 7:30, and then start working on the lab for 15 minutes. Let me grab that Stack Overflow. C++, dynamic, 2D array. Geeks for Geeks, that's probably good. Let's see what they use here. Malix, okay, whatever, that's fine. Okay, so this is more or less, right, so no, they're not using a star. I do not like this one. Let me try to find my Stack Overflow. Good, good. All right. Not constant, so we can't do that. So here we go. Good old star. All right, so this means it's an array of pointers. And this builds up your array. So we're not using compile time constant because the user is specifying how big things are. Drop that into the chat. Lots of direct messages. I can scroll back for everyone. There we are. All right, star. That is the key. All right, so go ahead and take the 5, then lab for 10 minutes. Going on mute. All right, just gonna do some quote unquote pseudocode. Give you the idea. Just make sure that we're more or less on the right path. Let's see. Do. See, I remember my array syntax in C#. New int. Let's see what I broke. Didn't break it. All right, so obviously in C++, everyone hear me right? I'm not on mute talking. Okay. C++, you're gonna do create your constructor a little bit differently. Syntax wise, but more or less, this is the idea of the matrix class. I'm not going to plug in the details for the set points, but the thing we want is our labels. Right, so I'll just keep that separate for the moment. But we want the user to create a value, so we'll get the number from the user. And then just create the matrix based off of that size, as well as our labels. All right, create labels, matrix. All right. Why does it give me a red squiggly? What did I forget? Does not take a constructor, that takes one argument. It's always fun going back and forth. All right, how big is the graph going to be? 5 vertices. It's going to say 5 vertices. For the print, is something like this. I less than size I plus plus. In fact, I is a terrible name, right? This is the row. Going row by row. And for int column equals 0, column less than size, call plus plus. And we'll just spit out the value of our array at that given row and column type thing. Plus a little bit of white space. All right, it's gonna be a bunch of zeros for the moment. Based on however big the matrix is. So assuming things are going to work, right, it prints out the matrix. 5x5 set of rows of all zeros because I haven't plugged in any code that would set the values. Okay, so that magic is going to be with our labels. So we would add in here, ask them for a string for each label, and then it's just a matter of finding where in that array of strings the label exists. Whatever the index is, that gives us the row and column. So the index of the first entry, if they say A, that's the row, then they say B, that's the column. So A is at row 0, and then B is at column 1. Let's do an alt click here. Not quite, but right. So that gives us to this particular cell. So we just index into that array and then set the value. So we just need to add in a function to do that. So the way I have this now, the array, I would just pass in the array labels, or we can fold in the array labels into the matrix itself. I'm not particularly concerned with your object-oriented design code here. If you want to just do global functions, it's fine. And the only real big difference between global functions and object functions is the object already has the context. You don't have to pass it to your function. That's the idea. Okay, carrying on. All right, so back to our adjacency list. How are we doing with our 3 examples here for the graph and what their corresponding list looks like? Looks like a graph. Very boring graph. Okay. Oops. Murdered it. No, I don't want to be suggesting. Okay. Kill it again. All right, guess we got to recreate it. Oh, wow. Okay, get out of suggestion, back to editing mode. It's always fun when you do new things that you're not familiar with and then bumble through them. All right, so A was connected to B and B is connected to A. Let's go ahead and do another graph. Key is to learn as you go, bumbling through, right? Of course, I chose to flat out ignore whatever the suggestion mode was in this particular instance, because it's not going to help me to make suggestions to myself. All right, so this will be a digraph. Some of these edges will be directed, and some will not, or rather, not singularly directed. So the matrix, however big, however number of vertices there are, that's how big the matrix is going to be. So it's a square matrix. As the number of vertices grow, the squares, right? So 4 gives you 16, 10 gets you 100, 20 gets you 400. So it grows fairly quickly, right? So A has 2 edges incident with it, one going to B and one going to D. One going to B, one going to D, and we can set 0 to all the other values in the row. B to A and B to C. B goes to A, B goes to C. 0 for others. C. Okay, notice that these 2 are inbound arrows, so nothing's happening there. So we have 1 outbound to D, and everyone else is 0. D, same thing, just 1 outbound arrow going to C. All right, so the digraph, we need to count the number of edges. This counts as 2. AB's 2 edges. 2, 3, 4, 5, 6. We should have 6 edges turned on. 1, 2, 3, 4, 5, 6. All right, so double checking. A digraph is counted 1 time in the matrix. So the same total of ones should match up with the edge count. All right, so same graph, this time with adjacency list. Texts. And we need to add 1 here, right? So we went from 3 vertices to 4, so this array grows by 1. And then the size of each list can be driven based off of however big to attach. Okay, there we go. However big, however many connections there are. That's nice and big. Let's print the graph. All right, so let's build our connectivity. So A connects to B and D. So we'll have B and D in its list. B connects to A and C, so we'll have A and C in its list. All right, C has D and D has C. C goes to D and D goes to C. All right, so 6 edges, 6 entries in total amongst all 4 of the lists. Let's see. Thank you. A goes to B and D. There we go. Copy, paste, and fix it. All right, 4 people correcting me, so that's a good sign that things are starting to line up. Yeah, so order matters. For a given visual representation, that's a specific list or matrix because the array is alphabetized and the lists are alphabetized. Sorting the array means we can binary search into here. So I would search for C, so we can do a binary search in here, right? So we got 100 vertices in here. We can do a binary search, right? So we can optimize finding the list that I want to work on by doing a binary search instead of a linear search. And the same thing with the lists. I can't do a binary search because they're lists, but we can stop searching. If I want to see if A connects or if C connects to A, right? I go to D's list and I can stop. I look at the very first value and I can see that D is greater than A. So I do not need to keep going down the list of however long this is to find out that the answer is no. All right, so if order matters, then it needs to be ordered. If order does not matter, then data can fill as it happens to come in. But more often than not, order is going to matter for 1 or more operations, so we will apply order to avoid as much chaos as possible. Let's see. That's a digraph. Now we have, let's see, what was the order I did? Let's do it in the same order. Weighted graph, okay, weighted graph. All right, so as we get some weight in here, the matrix and the lists need to update to account for the additional data points. To see if I can select all these at the same time and clear that out. All right. All right, so our AB edge 6 has an arbitrary value. AD has a 3. BC is 4. 4, get rid of this extra edge there. And DC will be 2. Okay, so our matrix still 4 vertices. All right, so we'll upgrade from a bit as the cell type to an int to represent the weight. So 0 indicates still no edge, non-zero, the corresponding weight of that edge, for that edge. All right, so we'll get our 4x4 in here. Label in alphabetical order. All right, A goes to B for 6. Since this is a simple weighted graph, I can just go ahead and do the mirror. All right, A to B or B to A, same difference. A goes to D for 3, A to D for 3, the mirror. Jump over to B, already did A, so I can go C, BC is 4, BC 4, BC 4, and CD2, 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 and everything else is a 0. Right, so we should have 8 values that are non-zero, or 8 cells are non-zero. We have 2, 4, 6, 8. So that's good, and should be mirrored across since it's a simple weighted graph. All right, so for our list, need to add in some data. All right, so ABD is good, B, AC, that's still good. C needs to add B. C goes BD. And D needs to add in A. All right. And I'll probably need to make all these boxes bigger. And A gets to B, right, for 6. I have enough space. And A gets to D for 3. And not quite enough space. All right. All right, so same thing here. The cost to get from B to A is 4. Let's try that again. 6. B to A is 6. So we come over here. Say there's 6 there. The cost to get from B to C. Look at our graph. Where is C? There's C. C is 4. So we'll go ahead and put in 4 over there. All right, same story. C to B. It's the reverse direction. That's 4. C to D. That's a 2. D to A, 3. And D to C back that way is a 2. All right, so more data. Just need to expand the node type to account for the weight. Inside our little edge nodes. And then we're Good to go. As our graphs get more complicated, same thing. So weighted digraph, same idea, except you're not mirroring the edges. Multi-graph. All right, so if we're just doing a simple multi-graph where we're just doing how much connectivity there is, right? Like doing a little organic chemistry. How many hydrogen bonds are there between these cells? Is it a hexene ring or a hexane ring, right? So you're counting the connectivity type stuff. So if we just have our weighted graph, same idea. Not weighted graph, multi-graph, multi-graph. And it looks just like a weighted graph, except we count the number of edges between a pair of vertices. Just don't grab that one, bring it over. And so we'll do, I guess we'll just do one of these. I'll need two. All right, 3 vertices, so 3 by 3. All right, so we have HS, LA, and Y. HS, A, and Y. No connectivity in the diagonal, so I'll just zero that diagonal out, help give me some markers or reference points here, right? So HS to LA has 2 roots. HS to New York has 2 roots. LA, HS 2 roots. LA to New York has 3. Right, and then just mirrors those last 2 values. Same idea with our adjacency list. Doing our counts. So we have here HS, LA, and New York. All right, HS gets LA 2 ways, and got to New York 2 ways. And let's see, LA gets to HS 2 ways, and to New York 3 ways. Hopefully my memory is working well. Yeah, I suppose we could. No, it's a singling list. Best to draw with the arrow. Yeah, that is the hardest thing with adjacency lists is I think that HS is connected to New York from this set here, but that's not what it means. It's just a collection, right? This is just a set of values. You can view this as a comma separated list if you wanted. In fact, I can just draw off to the side here once I finish updating this, right? So New York gets to HS 2 ways and to LA 3 ways. All right, so let's do that. It's a comma separated list. HS, which has A2 and Y2. A, which is HS2, Y3, and NY, HS2 and LA3. All right, it's a list. And flying off the screen list. Oop. Squished it a little bit too much. right? Both this textual representation and this list are the same thing, except this is an actual data structure, right? So we're drawing out the data structure as boxes and lines, whereas this would be like if you just dump it to the screen, right? If you were to do a screen dump of this adjacency list, this is pretty much what you would spit out. Okay, so that was our multi-graph. We had weighted multi after that. Weighted multi-graph, right? So it's still the same idea. We just need to increase the complexity of our element types. Weighted multi-graph. No, I do need that. It's got my numbers. All right. HSLA New York. HSLA New York. And we still have zeros on the vertical, or rather the diagonal, because it's not a pseudograph. All right, so representing multiple values. All right, LA to New York, 3 values. LA to New York, 50, 60, 70. We just need to have all the data points in there. All right, HSLA is 15. HSNY is 25. And mirrors. All right, so this node type probably just going to be an array. All right, so or a linked list, depending on if we expect edges to keep on coming along. Right, if edges keep on coming along, fixed size arrays tend to be a little bit problematic because they're fixed size. So you have to either resize them, so you have to add logic to resize the arrays, or you just go with a linked list and just keep adding in as appropriate to the data points in there. Whatever the data is, you can just increase the complexity of the element type to account for the additional bits of data. Does the data itself need to be in order? That's beyond our interest level, because now it's within just the data that we're giving back to the user, and it's not driving the structure itself. But usually this being ordered is something that you would want. So best to err on the side of the data should be ordered. Let's see, I have from my pseudograph. Didn't draw a pseudograph. Well, let's draw a pseudograph over here. Pseudograph. Now I need to get some links on some definitions. We'll see that there are some varying definitions for some areas of graphs. And we'll point those out. We try to operate in the realm of consistent based approach. All right, let's see, let's get a curve here. And good enough. Let's see if I can fix these up a little bit. And not really. All right, good enough. Class 0, S1, and S2. All right, so it is a directed graph, and these absolutely horrible looking single node loops is what's bringing us into the pseudographs. S0, S, S1, S2. All right, so there exists an edge from vertex S0 to vertex S0. There also exists from state 1, 0 to state 1. This one does not go back, but it can cause something can happen because it's to stay where it is, and then goes to S2. And S2's got a bunch of zeros for that row. And that's how we represent our graphs in memory. Now, all right, so a highly disconnected graph be wasting a lot of space in the matrix. But the list is more compact. On the flip side, a highly connected graph takes the same amount of space as any level of connectivity, whatever, in a matrix, but with an adjacency list. Those lists are getting longer. And those are nodes, dynamically allocated, and have the pointer maintenance. Maintenance and size. Right, so as is very often going to be the case, the greater your understanding of the data that's being modeled can help drive better decisions for the appropriate data structure to use for that data. All right, so if we're expecting graphs to be sparsely connected or lightly connected, then we have a bunch of empty cells in the matrix, less useful, but the lists, right, especially if they're empty lists, then there's nothing there. But on the other side, it depends on how we want to navigate the data. Arrays have random access. If I want to see what the value of this cell is in the matrix, getting there is easy. With the list, right, we do have to traverse down to see if it exists or does not exist. So there's pluses and minuses with any approach that you might take. All right, let's see. Graph shapes. All right, so some graphs have characteristics that apply to the graph as a whole. All right, some examples. our cycle graphs, wheel graphs, star graphs, complete graphs, and bipartite graphs. All right, so a cycle graph is basically a ring of vertices where you need at least 3 vertices to make the cycle, basically polygons. The degree of every vertex in a cycle graph will be 2. Let's see. The notation is C of n. Let's see if I can. Nope. Get my little subscript to work. Subscript, comma. All right. Try that again. Get a circle. All right. So there's a C3. And we'll expand up to C4. And we'll grow to a C5 second here. All right, so triangle, rectangle, and pentagon. More or less, of course, we draw them. It's going to be a little bit arbitrary. All right, so for example, these are all going to be C4s, whether they're looking like a rhombus or whatever. What the shape actually looks like is independent. What matters is the degree of all these vertices are very much 2. And some C5s. All right, what is next? Wheel graphs. Do star graphs actually. Star graph. It's going to be a collection of, see, it's going to be a central point with all other vertices radiating from that central point. Right, it starts looking like a star. You get 2 4 vertices, but some authors say you can have an S1 and up. Just kind of weird. So here's some example star graphs. And I'll start from where it actually starts looking like a star. And we'll do the same thing as well. Oh, big lag. And draw in the same graph in numerous ways. And so the first one's an S4. And we'll just go up to an S5 and S6. Yeah, and this one's a single vertex. I'll bring up a website. We can take a look. Wikipedia. Right, so we're going to take this S4 and just move that vertex over there. Right, it's still the same graph, other than my lines being all wonky. So, right, we could draw a tree, a 4-area tree sort of thing. And didn't meant to do that to a copy. Let's try it again. Let's copy and paste, then manipulate things a little bit there. Right, get the idea. So here we have S4s. And here we have an S5. And an S6, right? So the subscript notation tracks the number of vertices in the graph. Wheel graph. Basically, you take the star graph and wrap a cycle graph around it. I forgot to mention the degrees. So we have the degree, the perimeter, vertices are all one central vertex is the number vertices in the graph less 1. And the notation for that is by my pipes, where are you going? Pipe V minus 1. That's the degree of our central vertex here, and our S4 is 3, and a 1, 1, 1 for the perimeter, whichever way we draw it. Our S5, 5 vertices in the graph. Degree of our central vertex is 4, and it keeps on going from there. And S6, central vertex is 5 because it's connected to 5 perimeter vertices. Yeah, it's not absolute value, but it is the same operator. So in graph notation, the pipes indicate the count of vertices, or the edges if we're using E instead of V. The center is the number of vertices in the graph, less 1. And here's how we notate that. So whatever this number is, whatever n is, n minus 1 is the degree of the central vertex. All right, so the degree of the central vertex is V minus 1, and all others are 3. So let me grab my star graphs. Change my S's to W's. And we will wrap them up with wheels. All right, so a triangle as before, it doesn't work so well as a wheel. So we need to increase the number of perimeter points. And the bigger our perimeter is, the smoother the ride will be for that given wheel. And a bit of a curved connector here. That one, and form the perimeter. Smooth that out a little bit. Right, so with the W4, everyone has a degree of 3. There's a question, can we say it's a cycle then? The graph contains a cycle, but it's not a cycle graph. Right, this graph, wheel graphs have lots of cycles. Right, I can take any 2 perimeter vertices and then jump to the middle to create a cycle, or we can just go around the full perimeter to create a cycle. Right, so a cycle is when you create a path from vertex A, B, C, and then back to A type thing, or BDX back to B. So you can form a sequence of vertices where a vertex is going to be repeated in that sequence. And it doesn't necessarily have to be the starting and ending. As long as you've seen the same vertex more than once, then there is a cycle on that path. And if that path has a cycle, then the graph has at least a cycle. All right, so the W4, the degree of everyone is 3. W5, degree of everyone got 3, 3, 3, 3, and then the middle has 4, which you can also see up here. And then W6, right, 3, 3, 3, 3, 3 for the outside, and then we have 5 for the middle vertex. I add some color here, so let's see what the middle is. That's the middle. Our middle vertex. Here, arbitrarily, any one of these could be the middle vertex, but which designates somebody as the middle. Yeah, we'll get to Euler and Hamilton later. Those are characteristics that a graph might exhibit. Complete graph. Complete graph requires every vertex to be connected to every other vertex. All right, so this is going to be a highly connected graph. And so the degree of each vertex is going to be the number of vertices less 1. Right? Count everyone else but yourself. Oh, I forgot my notations here. Oh, I got player W's, S. All right, so here it's going to be a K because C is already taken for cycle graph. All right, so we can start at K1. It's a vertex. It's connected to every other vertex that it could be connected to, and there aren't any. So there's not a whole lot to be connected to. K2, there's only one other person to connect to. And K3 is the same as the C3. K4, growing up a bit. All right, so starting with my K3, grab a vertex, right? So we're going to add a vertex to our existing graph. So adding this vertex, it needs to connect to the 3 existing vertices. So our connectivity grows quickly. Same thing, K5, take vertex, add that vertex, and it's going to have to connect to all of the existing vertices in the graph. Let's see if I can get that one to connect without overlapping. And so it adds 4 more. All right, so it's a little bit of a pyramid here. Kind of hard to visualize where my links are, but that's the idea. Our K1, our K2, and growing up. Right, so all these notations, the number that is next to the letter for the graph represents how many vertices are in the graph. And that's what you have. Let's see. So cycle graph. Right. Back. Let me just grab these links. Just all right. I already had these links in the other document, but might as well just add them here as well. Right. CN. It's just big old cycles, basically polygons, nothing very exciting. And let's go over to our wheel graph. All right, see we're consistent here. W4, 4 points, W9, 9 points, right? Ferris wheel, more or less. Then we'll get to our star graph. All right, so here they're not consistent with themselves, and you can see they point out here. Some say this is an S8, which is what we say. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 vertices. So we want it to be consistent with all our other ones. And let's see, let's like that one's changed as that last, but so be very careful. This is one of the ones where there's 2 ways of saying the numbering. Our numbering is the vertices is the same as the number. Let's see, was it the Math World? That's the one that likes to say, here's an S1, right? So there's our little S1. All right, so since graph theory existed well before computers, right, it exists as a mathematical concept first, and then computers came and said, oh, we can do your algorithms a lot faster than you can as a human, so we need a way to represent these inside the computer system. Right, so right, if we were going to go with that one other definition, they'd be saying this is an S0. Right, so it's a 0-point graph. Right, so I don't know what you prefer, but we like, or at least I like consistency. The number represents the number. The middle or the outside being different is just the characteristic of the graph. It shouldn't have any bearing on the subscript for how big these graphs are. Let's see, did I grab star graph already? Drop that in here. Complete graph. Right, just connecting everyone to everyone. And then we need to get to bipartite. Right, so you see here, vertices are going to be collected into 2 sets. And the rule is, if you're a vertex in the first set, you cannot have an edge between to any other vertex within that set. So our U set here, U, V, A, B, W, X, whatever you want to label sets, that's completely arbitrary. 1, 2, 3, 4, 5. These 5 vertices will have no edges amongst themselves in set U. Set V, same thing. Of all these vertices, no edges can exist to the other set. All right, so what time are we at here? Let's see. Yep, okay. Bipartite, which I always try to hyphenate. Google always corrects me, so I'm finally remembering. All right, so the graph vertices can be grouped into 2 sets, A and B, such that set A does not have any edges between nodes in set A, and the same story for set B. Right. Yes. Someone's pointing out. Yeah. So, I'm curious. So someone's pointing out that their math book is showing the different numberings here. Let's see what we got here. All right. So this one. So Wolfram math here. K2, K3. It's the number of vertices. I wonder if there's others. What we have in this one. Well, those are not complete graphs. Yes, terminology. It's always fun. Right? It's consistent with ours. I believe the number of vertices is the more common definition. For wheel graph, sure. That's yeah. Wheel graph and star graphs are similar, so you can see why there would be the two standards. So our standard is simple. The number, regardless of the letter that's to the left, is the number of vertices in the graph, right? Consistent. And because there is that ambiguity, I won't ask it on the test because it just creates problems. So if I were to draw out a matrix and I ask you what the shape of this graph is, right? It might be a general graph because there's no shape, or you might see there are 2 entries in every single row, which means it's a cycle graph. Or you might see 3 entries in every single row except for one, which is fully connected. So you have a wheel graph, right? So whatever number you want to associate to that WN, the nature of the graph is the nature of the graph. So we'll roll with it that way. Right, so
Professor, could you explain the wheel graph again? What you were just saying about the wheel graph?
right, so the wheel graph, degree of every vertex on the outside is 3. And the degree of the central vertex is however many there are on the outside. Some authors, so here we got this first 2 graphs are W4s. Some will say that's a W3 because it's going to count just the perimeter vertices and say the +1 for the center. Right, so the wheel graph and star graph, some will take these numbers and say +1. Right, so for the purposes of our class, it doesn't really matter because I'm not going to draw a graph and say, is this a star graph, yes or no, and this is an S5 or an S6 because it doesn't really matter at that point. What matters is it's a star graph, or it's a wheel graph, or it's one of the other shapes.
Thank you.
Okay, no problem. All right, so let's draw out. What are they using for symbols? We're saying it's B, whatever, we'll just call it B. All right, so set A, 2 vertices. Set B, 3 vertices. And we won't bother labeling. Labeling just arbitrary. So set A on the left, set B on the right. Also arbitrary. And we can connect these however we want. So we'll do several. Set B, okay. And move these a little closer. So it does help to have at least some connectivity. We can go length. So plus this little edge floating or edge vertex floating wherever it wants to be, more or less still meets the requirements of not connecting anyone too much in the same set. Just too little that time. Up to the point that we are fully connected. All right. All right, so this is gonna be as fully connected as a vertex can be and still be bipartite. This is where we go over to being a complete bipartite. So let's actually copy that. Complete bipartite graph. All right, so it combines rules, complete graph with the rules of the bipartite graph. So bipartite restricts us for the edges, and then complete comes in and says connect as much as you can. All right, so here we have a K23, K23, and I can't use subscript in here, so I can do it. Just pick up. All right, shrink my text box. And we get smaller and smaller. In fact, we can go to a K12. It's kind of superfluous. And let's shrink it down. All right, so let's shrink this down. K12. One vertex over here, and it connects to everyone that it can connect to in the second set. All right, K23. Two vertices here, so it's got 3 connections coming out because there are 3 in the other set. And we can grow it as much as we want. All right, so the degree of every vertex in set A is equal to number of vertices in set B and vice versa. All right, so the purpose of bipartite graphs is when it makes no sense for links between values the same set, right? Common problem being a job allocation strategy. Right, so you have a group of workers, each with varying skill sets and a collection of jobs to be completed. So let's go ahead and get one of those going. Yeah, I need to make all this a lot bigger. Okay. All right, let's go for. Got Anna, Bob, Carla, and Dan. And we have. Someone's going to install toilets. Someone needs to lay the tile. Got water line, got lighting, etc., so on and so forth. All right. All right, so different people might have different specialties. But anyone can lay tile type thing. Bob's plumber, so water line toilets is kind of what he does. And these are varying data relations. Often you'll have data on the edges as well with weights saying, Anna's never installed toilets before, but you can read a manual and figure it out and do it in 8 hours versus Bob takes 2 because, he does 12 toilets a week on any given week. But the objective is we want to get the job done as quickly as possible with the resources that we have available to perform the jobs. And even if Carla is the best person for all these jobs, right? Let's say it takes Carla 4 hours to do every single job, right? That means it takes them 2 days to do the job, but the objective is get the job done one day. So you have, right, a couple people working on the tile, one person working the lighting, and one person doing the toilets, all concurrently to achieve the shortest completion time that we can get. All right, so bipartite says there cannot be an edge between Anna and Bob because that's irrelevant to the data at hand. There's no edge between the toilets and the laying tile. We're saying those can be done in any order independently for this particular job. Right, the lighting and the water line, we definitely don't want any relationship at all between the lighting and the water lines. Best when electricity and water does not mix together. And that's all bipartite saying. Right, if every single person is able to do every single job, then this graph would expand out to being a complete bipartite graph. Well, this is a non-complete bipartite graph. You can see Dan only knows how to lay tile. He doesn't know what a monkey wrench is, has no idea what ohms are, volts, watts, all that fun stuff. And he just thinks toilets are gross and says, I won't install toilets. This to become complete, Dan has to add links to all, right? Anna needs a couple, Bob needs one, and Carla needs a couple as well. All right, let's go ahead and take a 5-minute break and then we'll swing back. Okay, let's go dig up modules. Go over our terminology page, make sure. Right, just talking about vertices and edges, all the good stuff. Remember, if it's an arrowhead, it's directed. No arrowheads, that means it goes both ways. And Wikipedia has all kinds of good stuff to dig into. Right, we don't do the incidents one, but that's the other common way to represent. Yeah, we'll get to traversing. How do we search around through our graphs later? Let's see. Okay, this hopefully everyone's had a chance to go over a few of these. I don't recall there being anything terribly complex there. As usual, if you have questions, leave our links up here. Let me know. How are we doing on the terminology? Any questions about the various terms? And graphs doesn't have quite nearly as many as trees did. Basically, you're adjacent or you're not. You connect to me or you don't. That's about it. Okay, let's go back to our pseudocode again. And fold in our labels. All right, so the user is just going to go ahead and populate our array of strings based off however big it is. So we'll loop unless however big our matrix is. Ask them for our label. Oops. And then just set that into our array. And the other thing we're going to need is a function that tells us where in the array that particular label is. All right, so it's basically just a for loop, which .NET has a helper for me to get that. That just tells me where in the array that given label is. And right, sorting or not sorting, it doesn't matter. It's going to change how the values get dumped out, but not change a whole lot much other. So let's see what I broke my code here. takes one argument. Oh, yes, I should. Get what it needs. So the next step is just basically adding an edge from vertex and string to vertex. Int row equals index for our from vertex. This is actually a keyword. Anatomy. Nope. Okay. And then our column get index from where we're going to. All right. So if this is a directed graph, what do I call my array? Array. Very creative name. My row call is on. That edge exists. To make it a simple graph, we just flip it. And now it's a simple graph. Are you mad at me? Semicolon. What's going on here? 5K, red squiggly for no reason. It's always fun. No, I think I called it lowercase array. Yeah, it's just array. It's just being weird. Okay, so now my program needs to assign. All right, so here's my original. Set the labels, gets the users to populate it all, and then just do loop to get some edges to be set. While true, I'll just put a break in the side. Ask them for 2 points. Add an edge between. All right, so string from vertex. Line. If from vertex equals -1, we just break out our loop. Otherwise, we'll grab our 2 vertex. And then from there, we can just add our edge. From vertex to vertex. And we'll dump it out just to verify that things are making sense. But then we do need a print that actually prints labels as we're asking. So we'll start small just to make sure things are working. A and B. All right, so there's AB, got turned on. And you did it as a directed graph. Yeah, all right, -1. Get me out of the loop so I can highlight. All right, there's our little AB. That's more or less what you want to do. And slice it, dice it, whichever way you want. All right, sorting doesn't much matter. You just call the library queue sort at this point because the purpose of this lab is the matrix. So feel free to use library sort now, or go grab go grab. Not logged in. Why enter logged in? Says I'm logged in. What? It's saying I'm not logged in. Okay, let's go duplicate. Try to save again. There it goes. Little bugs. Right, obviously, this is C#, so this pseudocode won't work in a C++ compiler. So we'll change the make. Plus, you need to change how you dump out your matrix to the screen, but my dump's just sufficient for showing that things are working. And as it stands, if I want to add a point between D and D, right, it's totally allowing self no loops, right? So we're not enforcing any graph types or shapes onto it. If it ends up being a cycle graph, it ends up being a cycle graph, but it's just, we're just doing general graph support. Be it a pseudograph, simple graph, direct graph, multigraph, whatever. Well, I guess we're not supporting multigraph in other ones because it's one or not. If we wanted to make this more intelligent, we would give greater capabilities, right? If we want to support a multigraph, right? Now we can set the same vertex twice. Right, A and B. Oops, I totally killed my second label. All right, let's try that again. Two vertices, A and B. Connecting A and B. There's A, B, connecting A and B. Now it's two, right? So now we have multigraph support. Right, so if we wait would be another expansion, right? So depending on the complexity of the graph types that we want to support, our code needs to expand to support it. Right, so instead of adding one, we'll add the weight. So this wouldn't support weighted multigraph as it stands here because we're just adding the weight in. So if we had a 3, a 5, and a 9, right, we'd add that together to get, say there's 17 there, but the matrix doesn't know that that 17 is 3 separate edges. And that's where our data type needs to get more complex, where we come along and define, right, an edge, weight, and we just have it be edge next type thing, like this type of idea. And that's just each element's an edge. So when the first one comes around, we have to new it up to make it exist. Give it its weight. The next would be null. And now they can add in multiple edges. But the basic foundation of the code is still largely the same. Yeah, we can use the last 10 minutes. Wait, yes, that's right. 10 minutes working on the lab. It's come on line 13 mean. That just means it's a matrix. That's C# syntax for doing multidimensional arrays. All right, so we got use the last 10 minutes to work in lab, and the last remainder of class is break. No, my code does not show AB because my code just has dump. This is not the entirety of the lab. It's just large swaths of it. See a bunch of chatter in Discord. So I'm gonna check what's up there. Yeah, it's just a two-dimensional array for the matrix, but you need to track the labels. And since it's the same labels for both the horizontal and the vertical, we just need the one array to track the labels. All right, string, we want to do just a single string of appending characters. Have your vertices just be single character names. That's perfectly fine. Well, you don't need to use string stream. you could just use a string that you just keep appending to, and then just do an index of on that to get the character to represent where the label is. Right? I mean, obviously it's better as an array of strings, but I don't care about the labels because that's just the data part. What matters is the structure part. All right, any last questions? Go on mute and stop the share, but I'll still be floating around on audio in case you have anything else. And then floating back around on Discord.